Today we have our last lecture where we talk about one of the specific type of generative model, which is called generative adversarial network. So far in this course, we talked only about classification problems and just a bit about the regression problem. Those are kind of machine learning problems or methods that are called supervised. And the basic characteristic of the supervised methods that for each data point in our data set, we have associated features and labels. So for the classification problems, we have labels that are of categorical nature. For example, for binary classification problem, we have a classification to dog images or cat images. Then we have multi-class classification where there are more than 2 categories or classes. And there is also a multi-label classification where each data point can belong to more than one category or class. And for regression problem, the predicted labels can be of the, they are real valued, so from -infinity to +infinity. Those who been on our other course, machine learning with Python, also know that there are unsupervised machine learning methods, for example, as clustering and dimensionality reduction. For the clustering, we have a data set without any labels, and we want to find some groups or subgroups within the data set, which are going to be divided or grouped based on some notion of the similarity between the data points. And dimensionality reduction is happening when we have data with high dimensionality, and we want to reduce dimensionality of this data in order to be able to either, for example, visualize the data. So in this case, we want to reduce dimensionality of the data to, for example, 2D or 3D, so we can plot some sort of images or graphs of the data. And also maybe sometimes we want to reduce the dimensionality of the data before we feed it to some other machine learning methods. So we want to just get rid of correlated features and only get most important features of the data set. So as I said, basically what we've been doing so far, we've been getting some data set. For example, in this case, there is an image, and we feed this data set or data points to the artificial neural network, and we ask to predict the label, either categorical label or real valued label. Today we're going to discuss different kind of network where we want to teach the neural network to produce the data that we want to. For example, if we have images of the dogs in our training set or the target set, we want to teach the network to produce this kind of images. And this is the types of the model that are called generative models because they are generating data samples. There are many different ways to produce the samples, or there are many kinds of generative models in machine learning and in deep learning. But today we're going to discuss only generative adversarial networks, or GANs. And the GANs has been inspired by the principle from the game theory, which is called zero-sum game. And in this slide, it's kind of a simple illustration of what is the zero-sum game. So you can imagine that there is a game with 2 players, player number 1 and player number 2. And these blue and green circles represents the event space for the player number 1 and 2. So they represent what objectives or the goals of each player. So for the non-zero-sum game, there exists situation when both players can win. So there is a win-win situation. For the zero-sum game, there is no such situation exist. If the player 1 wins the game, it means automatically that the player 2 lost. And vice versa, if the player 2 wins the game, then the player 1 automatically lost. So how this principle of zero-sum game can be used to create a model which will generate the data. So imagine a game where we have 2 players, and one of the players is the generator or artist, and another player is the discriminator or critic. So in the first rounds, in the beginning of the game, the generator produces some kind of samples, and these samples are not very good. They're usually some kind of noise, or they are very random. And we also have our target sample that we want to produce. We take these very noisy generated samples, and we take these target samples from the training set, and we feed it to the discriminator. The only thing that discriminator do is to classify these samples as fake or real. So in this case, the fake samples means the samples produced by the generator or artist. And the real samples are the samples from the training set or the target set. So in the beginning of the game, because the generator is so bad, it's very easy for the discriminator to recognize the fake samples. So in this case, the discriminator wins and the generator lose. After each round, both players get the feedback. So if the generator lost the round, it gets some sort of feedback that helps to improve the generated output. So after a few rounds, the generator becomes better at producing the samples. And now these samples are very similar to the training set or our target set. And now discriminator is kind of confused because these samples looks like real, and it makes a mistake and classifies these fake images or fake samples as real. So in this round, the discriminator lost and the artist won. And again, the discriminator also gets some feedback that helps to improve in the next round. So this game consists of iterations or the rounds where these both players compete against each other, and they are getting better and better with each round. And we're gonna talk a bit more about the implementation of this model in the TensorFlow. But first I want to show some examples of the produced data from this kind of network that compete against each other. And this is our samples from the original paper where this kind of network has been proposed in 2014, the paper called Generative Adversarial Nets. So you can see that those are produced samples trained, and the network was trained on the MNIST dataset. And actually the output is very good. You can recognize the digits. Then there's also generated faces from this kind of network. And some faces are quite realistic, some are not. So the result is a bit worse than for MNIST data. And below, there are samples generated from a CFAR dataset. So this is dataset with 1,000 categories of different kind of object and animals. And as you can see, the results are not very impressive. So this first original network wasn't very good for generating this kind of data. Since the 2014, since the publishing this first network, the GANs has progressed quite rapidly, and now there are a lot of different kind of generative models that are based on GAN, but they are like improved versions. And within each year, these GAN models produce the more realistic images or fake images. Here we can see examples of images of human faces. And you can see that the progress is indeed very visible. And just for fun, we can just see the generated images. This website calls thispersondoesn'texist.com. And as you can see, this image is generated by a GAN, and specifically by StyleGAN2. And if you refresh page, each time you will get an image of the like a fake person, which doesn't exist. There is also a version for the cats and for the horses. And if you check the version for the cats, it's quite reasonable. It's not perfect. It's a bit worse than the generator for the human faces, but it's still quite reasonable. The generator for the horses is not very good. You can easily see that it's the proportions are not very realistic from time to time. For example, here it's visibly fake image, but in general, it performs very well, especially if it's trained on a specific domain. These networks can produce not only images, but also audio signals or any kind of data that you want to. You will have more examples in the notebook. Here we have examples of a bit more complicated GAN. It's called cycle GAN. It consists of not just two players, two networks, but additional players or networks. And the idea here is to convert input image to the associated output image, for example, with the change pattern. So here we transform the horse to the zebra. It's not perfect. You can see that there is still some patches that are not covered by the pattern, but in generally it looks quite okay. It's not working perfect all the time. It depends what kind of input samples you have. For example, here, the network, the generator applied this zebra pattern not only to the horse, but also to the human and also to the rocks in the background. So it depends what kind of input you are using. So those been just fun applications of the GANs. And now let's see how we can actually implement these networks in the TensorFlow Keras. So what we're gonna do, we first create a random vector, or it's also called latent vector. So basically how it's created is you just sample all the values of the vector from the normal distribution. In this sense, that's why it's called random, because we are sampling from the distribution. We take this random vector and we feed it to the generator network. Let's imagine that it's just a simple feed-forward densely connected network. The generator then outputs the generated samples, which are then fed to the discriminator together with samples from the training set. Then the role of the discriminator just to classify the samples as fake or real. As you can imagine, this is pretty easy to implement in Keras. First, we decide what is the size of the random vector. Here we decide that it's 100. Then we have to decide what is the shape of the output sample for the generator. And then we can just stack dense layers, and the last dense layer of the generator should have this shape of the generated data point. Discriminator is also can be just a stack of dense layers, but the last dense layer should be for the classification, for the binary classification. So we have just one unit, one neuron with the sigmoid activation, which will return to us the probability of the sample being fake or real. So the more difficult question is how to train this kind of network, because we have two networks which are competing against each other, so they have opposite objectives. So we do the training in two stages or two phases. In the phase one, we train discriminator. So first we build or we sample a random vector. We feed it to the first artificial neural network, the generator. The generator produced some sort of output, the generated samples. In the beginning, it's going to be some noisy sample. And we also have a training sample or target sample, and we feed it to the discriminator. The discriminator classifies the samples to fake and real and returns the probabilities. And given our true labels, we compute the loss and the error, and we propagate this error to discriminator by using just normal backpropagation step. And then we tune the weights of the discriminator in a such way that it classifies better these real samples as real and fake samples as fake. In the phase two, we train the generator. We again sample from the normal distribution. We create the random vector, feed it to the generator network, create fake samples. But here we have to use a bit of a kind of a trick, because we want to fool the discriminator into labeling the fake samples as real. We assign the labels for the fake samples the same as like real. So it's the opposite from the previous step. Then we feed these fake samples with the switched label to the discriminator, and again, get the probabilities, compute the loss, and then propagate the error, but now to the generator. So we don't touch the weights of the discriminator, we only adjust the weights of the generator. So if the discriminator classifies the fake samples as fake, then the generator gonna be penalized. And if you want to understand a bit more how this process is going, you maybe want to take a look at the algorithm from the original paper that is in the notebook. But you don't have to like know these formulas or understand it. During the training, we will be just gonna using the normal binary cross entropy that we used before. But the basic idea that we can, by using the appropriate labeling for the fake and real samples, we can write this loss function, and we can minimize this binary cross entropy, and we can get the same formulation of the loss that was in the original paper. So it looks a bit different, but in reality, these are the similar formulations. So in this case, the objective goal for the discriminators is increase the probability put on the real data and decrease the probability that are put on the fake data. In the case of generator, the objective is the opposite. For the generator wants to put more probability on the fake data. And again, we just need to provide appropriate labeling. We need to assign the label Y1 for the fake samples in order to get this sort of a similar formulation that was in the original paper. How to do it with the TensorFlow Keras? First, we combine these both nets, the generator and the discriminator, in one model. And I will explain why we need to do that, for what purposes, later. Then we compile first the discriminator network just with the binary cross entropy and some optimizer. It doesn't matter what kind of optimizer. And then we compile the GAN. So before compiling the GAN, this model that consists of the two nets, we need to set discriminator trainable files in order to fix the weights of the discriminator. We need to do that for the generator training, this phase 2 step. And again, we just use normal binary cross entropy in some optimizer. Because this is a bit more complex model than we used to use before, we need to write our own custom training function. And we provide this GAN model, the combined model of these two nets, our data set, batch size, coding size, number of epochs. And for each batch in our original training set, we perform these two phases. The phase 1 is training the discriminator. So first, we sample from the normal distribution by TF random normal. And we need to provide the input shape, our batch size, and the coding size that we set, in this case 100. And thus we formulate this render or latent vector, which we call noise. We feed this noise to the generator, and the generator produces these fake samples. Then we just combine these fake and real samples in one batch by using concatenation. And then we need to create appropriate labels for the fake and the real samples. We will set y equals 1 for the real samples and y equals 0 to the fake samples. And then instead of using the feed function, we use train on batch function. This function or method is used when you do just one single gradient step. And we feed this batch with our created labels to the discriminator. And by that, we compute the loss, we backpropagate the error, and we adjust the weights only of discriminator. In phase 2, we train only the generator. And in this phase, we will need our this GAN model that we created. First, we again create a random or latent vector from the normal distribution. And then we feed it to the GAN model. And in this case, you should know that the labels are switched. So for the fake labels, for the fake images, we set the label 1, and then we feed this noise vector and labels to the GAN model. And when we apply the train on batch function on the GAN model, we again perform the single gradient update. But because previously we set the discriminator trainable false, it means that only the weights of the generator are going to be adjusted, but the weights of the discriminator are going to be fixed and unaltered. So in this case, we just need this GAN model to separate these two phases of the training.